Greetings all conference participants, conference chair and staff. My name is Charles and I will be presenting a research entitled Predicting SARS-CoV-2 Infectious Dissemination Patterns by Remove S and R Compartments from SIR model equation. I work at the Secretary of State for Education and Sport in Paraná, Brazil, and my research is designed to predictive methods concerning COVID-19 dissemination, that is, the use of SIR model equation and its variants. The research lots of question that's being very discussed nowadays concerning S and R the compartments of SIR equation due to the confounding scenarios of variables that sustain this model in order to make predictive numerical solutions for COVID-19 dissemination patterns. We can have a glance of how predictive methods are used when you see every day the cumulative daily new case of infection for each country, region, or place. Distinct patterns of dissemination are formed to each of these samples. So the question is, can we have a global solution for a given SIR model to every sample? If not, and if you check the latest research since the beginning of epidemics, you might find several types of SIR model equation and with its variants of every sort. For example, here we have an image from Center of Disease and Control and Prevention showing that uncertainty prevails in 21 SIR model equations. So I launch another question. Why these models present uncertainty? Why there are lots of models officially adopted and many others being generated in scientific literature? One problem we can assume is that the inputs of data are quite different from one model to another one, as well as the samples of analysis. So we have distinct scenarios of COVID-19 dissemination, and at that point, no homologous data can be found as far as the algebraic relation among the objects that compose the equation and the cause of the disease evolution. Consisting of this information, topological spaces might vary from many methodological assumptions, models adopted to explain the COVID-19 dissemination and spreading patterns. At that point, we don't have a unique solution, a global solution. And for every case, we should use a specific model. But more than every case, we need to understand how the time series data should be treated using a specific SIR model type. The susceptible and removed terms of the equation of SIR model find itself some limitations due to mainly variables and confounded scenarios that it creates, like policies range, individual behavior compliance, spreading patterns that could be aerosol, biosol, and ground forms of transmission. And for each of these spreading patterns, we might find dissemination patterns, the derivatives of these three main points that could be also extended to confound the scenarios of analysis as type and duration of health policies, health infrastructure, population genetics, human variance in terms of biological resistance, epidemic outbreak, infodemics worldwide in several scales, individual, community, government, media, globalization aspects, COVID-19 testing availability, reliability and timing of the outcomes for the SIR models used, virus mutation, citizen adherence to the social isolation or social distancing. All these confounding outcomes in each country pose a challenge to identify the exact SIR model equation that should be used. It was found in this research we conduct that COVID-19 could be divided in three regions of analysis. These three regions have specific variables that sustain the spreading and dissemination patterns. The environment region, where spreading patterns can be found initially with environmental factors influencing the dissemination. The policies region, at second point, that policies find its limitations after the curvature start to reduce, and in the urban spaces is a specific design of cities that sometimes the policies can pass through it, and policies remains as incapable of giving good results. This research didn't investigate the SIR model and its specificity of which SIR model is the best for each of the regions. I just put the regions, describe the regions, and now further researches are necessary to make this correlation. As far as policies are presenting worldwide an attractive solution to reduction of COVID-19 dissemination, this region was the first to be identified. Since we get daily data of cumulative new infections worldwide or for every country, we observe that if a country started a policy, it starts to reduce. So this region is very specific, and you can understand it in the daily news. You can see that urban space phases, sometimes the policies don't have an effective outcome that we expected to be since the beginning of epidemics, when it was started. Making the adjustment of SIR model equation, we got the normalization of data, the best fitted data for policies, the desired sample that we should retrieve the data, concentrated in the peak of the epidemic evolution. As shown in this figure, we have the population divided by the time in the specific region of analysis, since the outbreak of the epidemics until the last day of your analysis. And this formula used in the specific region of dissemination gives us, with a simple statistical tool, the mode, a very simple manner of seeing the outcome or predictive ways of understanding COVID-19 dissemination. The results show us, as these tables, these three tables, the sensitivity of 7, 19, and 30 days. We could understand that the white regions indicate that no variation were found in dissemination patterns. So these countries reached some type of policies that no more oscillations occurred, while the green lines, the countries are still oscillating. So if you get this data, the white and green lines, understand what policy started, what happened to the country, what are the data we can find here. We can have a predictive model of the COVID-19 dissemination and spreading patterns, mainly if we do future research to understand that regions of analysis, because these results are only for the policies region, the peak of the curvature. This is important. Why? Because we could track, as I said, the type and duration of policies with the best pattern format for each country, and we could make adaptations to the urban spaces of the others, or make better robust policies measures to make better results to be achieved. To conclude this presentation, we can put some constraints in the SIR model in its few compartment use that can fail to achieve global solution of prediction. And in the opposite direction, the method presenting this research tries to fulfill 4 points. The microprocesses under a given assumed local stability that is very, very random, the tiny machine learning or mathematical simulations experience of SIR models that find limitations, as I showed in the other slide, several uncertainties can be found, the empirical observations and data constraint that we have in the confounding scenarios for each of the samples, And one more problem is the privacy Internet of Things, that we cannot track in real time how the disease is evolving, but some tools as these, as it were created worldwide, mainly starting in China, with real-time data of mobile phones to understand if the individual is contaminated or not, exposed or not. There is some limitations of the study, that is, we don't have the cumulative daily new cases worldwide or in a country, because there is some delay of the governmental offices to give this data. I thank you very much, everyone, for this presentation. If you have doubts or any other comments, please email me, send me some comments at this contact. Thank you very much for watching.